All right, we're going to start a new unit on systems of equations. And in this unit, we're going to be doing some of the things that you've already done in Algebra 1, solving systems by using really three methods, graphing, substitution, and elimination. But then those were all done in Algebra 1 with two variables, and you had two equations to solve. We're eventually going to get to three equations with three variables, and then even more. As we add more dimensions into solving systems of equations. But what I want to do first is review what these systems look like. Hopefully this will bring back some memories from what you guys did in Algebra 1. But as you watch this video, I do want you to take notes because you're going to need these notes as you do the homework assignment that'll be due tomorrow. And so the first example that I want to go through with you in our notes is a comparison of, and I'm making these up, a comparison between Cedar Point and Kings Island. And what I want to do is talk about prices to get in, and I know they're not really this way, but let's assume that in order to get into Cedar Point, you pay $14 just to get in the park. Plus, you have to pay $4 for every ride you go on. So it's $4 per ride. That may or may not be a good deal, depending on how busy the park is. I've been at Cedar Point and gone on like 3 rides the whole day just because the lines are so long. So that might be a good deal in a situation like that. But let's compare that to a situation similar to Kings Island. Let's say to get into Kings Island it costs $32 just to get in the main gate. Plus, every ride you go on costs you $2 per ride. And what we would want to do is figure out when is it more advantageous for us to go to Cedar Point, when is it more advantageous to go to Kings Island, and then ultimately when would it be the same price for both places. And so one of the things that you're going to be asked to do is to be able to write an equation for both of these. So for Cedar Point, if it's $14 to get in plus $4 per ride, the $4 per ride is the slope. The $14 is what the beginning amount would be, which is the y-intercept, and we'd have an equation that would look something like this. Y equals $4 for each ride plus $14. And then at Kings Island, the similar equation, $2 is the slope, $2 per ride. So if x is the number of rides, it's 2 times x plus $32 to get in the park. And then if we're going to graph both of these on a graph, here are the number of rides that we go on, and here is the cost. If we were to graph, first of all, Cedar Point, and we don't go on any rides, we just walk around the park, it's going to be $14 at the beginning. So let's say this is 10, and this is 20, and this is 30, and this is 40 here. It's going to be $14 just to get in the park. But then every ride we go on, if this is one ride, it's going to be $4 more, so that would be $18. 2 rides, it's going to be up to $22. 3 rides, it's going to be up to $26. And it's going to be a linear equation that looks something like that. And if we were to graph Kings Island, just to walk in the park going on no rides, it would be $32. But then if you went on 1 ride, it would be $34. You went on 2 rides, it would be $36. You went on 3 rides, it would be $38. And we get a graph that looks something like this. We did something similar to this with the Olympic projects that we did with the men and the women that we wrote our own equations for, and a lot of us were able to figure out when those two lines intersected, because at the beginning it would be advantageous for us, at least cost effectively, to go to Cedar Point because it's a lot cheaper if you don't go on very many rides. But if you go on a lot of rides, then we're more in this area of the graph, and then it would be cheaper for us to go to Kings Island because it's cheaper per ride at Kings Island. But what we would want to do is figure out where these two lines intersect, and that would be the solution, not only of what would be at Cedar Point, but would also be the solution at what we would have at Kings Island. This is probably not the best example to do by graphing because the graph is going to be so big that it's going to be hard for us to figure this out, especially without using graph paper. But you might remember one of the ways, that we're going to get to this more tomorrow, but one of the ways to solve a system like this would be to use substitution. Here, if y equals 4x plus 14, I'm going to go to this equation, but instead of putting y equals 2x plus 32, I'm going to put what y equals over here. Y is 4x plus 14, so I'm going to replace this y here with 4x plus 14, and that's equal to 2x plus 32. So we can get the x's together. If I subtract 2x from both sides, I'd have 2x plus 14 equals 32. And if I subtract 14 from both sides, 2x is going to equal 32 minus 14, which is 18. And if I divide by 2, x is 9. And so it should be that if I plug 9 both into the equation for Cedar Point and the equation for Kings Island, I'm going to get the exact same price at both places. If I plug it into Cedar Point, 4 times 9 is 36, and 36 plus 14 is 50. And if I plug it in to the equation for Kings Island, 2 times 9 is 18, and 18 plus 32 is also 50. So the solution would be if I went over here to 9 rides, I know I'm skipping some here, it should be a cost of $50. And that would be the solution to this system, which is when the price of going to Cedar Point and the price of going to Kings Island would be the same. The systems that we're going to do in here are going to fall under one of 3 categories. Okay, and I'd like you to put these in your notes. They're either going to be an independent system, if there is, like this one, if there is one solution. However, if the 2 equations basically are the same thing, it cost $14 plus $4 per ride at Cedar Point and $14 plus $4 per ride at Kings Island, the cost is always going to be the same. In other words, the graphs would be right on top of each other. That is a dependent system. And in a dependent system, there's an infinite number of solutions, because every point on the graph would satisfy both equations. Whereas here, in an independent system, there's only one point that satisfies both equations. The third type is what's called an inconsistent system. An inconsistent system is one that has no solutions. An example of something like that would be, let's say it's $14 to get into Cedar Point plus $4 a ride. But to get into Kings Island, it's $32 plus $4 per ride. It would always be more expensive at Kings Island because the 2 lines would be parallel. They would never intersect. And so that would be a situation where the 2 lines would be inconsistent. In order to classify these, here's probably the best and easiest way to classify them. If you're looking at the system and they have different slopes, the lines have different slopes, you can tell right away that it's going to be an independent system. Because an independent system, like for example here, the slope for Cedar Point is 4, the slope for Kings Island is 2. Those 2 lines are eventually going to intersect at one place. However, if they have the same slopes, one of 2 things could happen. If they have the same slope and the same y-intercept, then they're the exact same line, and that is a dependent system. If they have the same slopes but different y-intercept, then those type of systems would be inconsistent. So it's really important to know which type of, you can pause this, sorry, I was off the screen and didn't realize it. It's important to know which type of system that you're going to be working with, because you want to know whether there's one solution, an infinite number of solutions, or no solutions. So let's just do a couple of these. Without really relating this to something specific, I want you to take a look at these 2 equations. Let's put down 3x plus 9y is equal to -9 as one equation. and the other equation is y equals negative 2x plus 4. If we want to solve a system that looks like this, by graphing, we're going to start by graphing both equations. So I'm going to start by graphing this first equation. And we could do this one of two ways. We can rewrite it in slope-intercept form, or I can make an x and y chart and plug in my intercepts. Or plug in zeros to figure out what my intercepts are. But for this one, I think I would subtract 3x from both sides. So I'd have 9y equals negative 3x minus 9. And if I divide everything by 9, then y will equal negative 1/3 x minus 1. So here's negative 1, and my slope is down 1 and over 1, 2, 3. Or up 1 and left 1, 2, 3. And the line's going to look something like this. If I graph this equation, my y-intercept is at 1, 2, 3, 4. Slope is negative 2, so I'm going to go down 1, 2, and over 1, down 1, 2, and over 1, down 1, 2, and over 1, and my line looks like this. This is an independent system that has a solution that is at the point 3, negative 2. Okay? We will, however, get other types of systems that might look something like this. First equation might be y equals 2/5 x minus 2, and the other equation would be 4x minus 10y equals 20. And if I were to do the same thing down here as I did in the first example, I'm going to rewrite this equation and put it into slope-intercept form by subtracting 4x from both sides. So I'd have negative 10y equals negative 4x plus 20. And if I divide everything by negative 10, then I'll have y equals negative 4 over negative 10 reduces to 2/5 times x minus 2. I want you to look how that compares to the very first equation. They have the same slope, 2/5, same y-intercept, which is negative 2. This has an infinite number of solutions and is a dependent system. So those are the types of things that we're going to be working with in this first lesson. I'm going to have you go through and take an online quiz on these concepts, and then you can work on your homework assignment in the next in this bundle. So hopefully that all made sense, and if it doesn't, we'll talk more about it tomorrow in class. Have a good night.